Thanks very much. Yeah. So if you've got any questions, I must admit, I think there's a sort of Q&A button there. I'm quite happy to take questions in real time. So I've just clicked it open for myself. So as I go, don't think that I'm just going to monologue at you. If I can see if I see a question, then I'll probably try and answer it in real time. That said, I will go forward and say, today we're doing a ZP webinar with Technando. This will be around electrochemical sensing. So I want to say a special thanks to Technando, who are today's sponsors and our excellent representation in India. The next slide is a slightly strange slide. Well, in fact, the next slide is actually the agenda. It'll be a very brief introduction to Zimmer Peacock. I'm not going to burn up all your time talking about us. A brief introduction to wearables and IVD, in vitro diagnostics. So as I say, this is a wearable system. It's something I will talk about today. This is a sort of multi-million-dollar type product. I tell my children this is $1 million watch, and it's no joke. In terms of the investment that's gone into it. We will talk very quickly about electroanalytical techniques for wearables and IVD, but I do feel like, especially in India, to be fair, people are extremely up on the science anyway. And if I feel like there's an interest, you can express interest in where you would like this webinar series to go. So if we could call this the first one in the series, maybe today's is an introduction. And as we find out where the questions are going, we may hold more in the series. At the end of it, I'll try to summarize it because this might be quite a eclectic webinar. I'll be respectful of time, so I can see we're 3 minutes into this, so I will, go fast. First of all, sincere congratulations, to be honest with you. When I heard that that India had landed, this probe on the mountains on the South Pole, I mean, and I'm sorry for the Japanese and I'm sorry for the Russians, but it's a real. I think the world has really, has paid attention, and it's all over the global news. So I just want to say a quick congratulations to the nation, basically. I mean, it is noted. It's an excellent achievement. If you find water, brilliant. Next webinar we might do from the moon. So congratulations to you and your country, guys. Well done. So biosensors are not to the same extent that landing a rover on the moon is, but biosensors are changing the game. Today, why should any of us care about electrochemical biosensors? Look, we can do, environmental monitoring. I know this is a big thing in India, and we'll talk about nitrate monitoring today, but I won't talk about nitrate monitoring that I've covered in the past. In the past, we have definitely covered nitrate monitoring in soil. Today, I'm going to cover it at nitrate monitoring in water. Healthcare applications. Lots of what we do at Zimmer Peacock is really about in vitro diagnostics and also wearables. I think environmental monitoring actually goes along with agricultural and plant sciences, and something that we're quite keen on at ZP, and it's not so much, it's just in general, and it won't be the focus of today's webinar, is the food and beverage industry. The food and beverage industry is a kind of industry that knows it needs to do testing. It doesn't actually do all the testing that it needs to do. And the reason it doesn't do all that testing is because the technologies that are available to them, let's say HPLC, high pressure liquid chromatography, let's say LCMS, liquid chromatography mass spec, this kind of equipment was designed for the pharmaceutical industry where they generally could afford that kind of kit. But a small producer of chili or ginger products or garlic products is not going to be able to afford that kind of kit. So that's also a market that's, addressable. And I think when I say you name it here, the world, we gave a talk this week to the tiny machine learning community, tiny ML. I think the world is really interested in electrochemical sensors because it's the conduit from biology through to data. So electrochemistry or electrochemical sensing is one of those sciences that really is at the edge of, we are human beings, and electrochemical sensors can integrate with us really well, and then they can essentially turn biology into electrons. Electrons become digital, and then we can kind of get information from that. So the topics of today: why should we care about electrochemical sensors? I'll make that point a few times. How are electrochemical sensors, improving the world? And I also want to talk about commercialization. I want to talk about the strategy to increase the translation of research. I'm sure this happens in the US, in Europe, and in India. There's too much research going on and not enough translation actually into products. And I think it starts almost, if you don't start the research off on the right foot, especially in electrochemistry, it will not commercialize extremely well. So if you've got any questions of ZP, this is our website. There's a contact button here, and it comes straight to us, and we're pretty good at responding. And also, this is the Technando website, and they have a contact button there as well. So you can get hold of in real time in your own time zone Technando, and you can also get hold of ZP. My name is Martin Peacock. I do recognize many of the names here today, so I won't emphasize too strongly, who I am, but I just want to say that, I founded Zimmer Peacock. I'm an electrochemist by training. I have an honorary research position at Swansea University, so I kind of span this academic and industry interface. This is ZP's 9th year of existence. We were launched in 2014. In November, we'll be 9 years old. We are ISO 13485. We do electrochemical sensors development and manufacturing, and we're primarily in the UK and Norway. This is the team. Some of you have seen this image before, so I'll be fairly quick. But I think within this team, there's something like 23 languages spoken, and people from all across the globe. And our facilities in Norway and in the UK are really kind of state of the art. And it's not that we don't want to be in India. I think through Technando we will come. It's just finding the right time, the right opportunity to do it. When I say come, I mean in a sort of manufacturing sense, not in a sort of just a visiting sense. So why are we here today? At least some of us are here today because electrochemistry as a science has already proven itself to be it can work in very dirty samples. This is blood. It can work in very tiny electronics. This is called a glucose meter, and it can be very fast. A glucose sensor works within 5 seconds. So everything that people would want for rapid testing is proven to work in principle just through the glucose meter. So at ZP, with simple hypothesis, glucose technology or electrochemical glucose sensing works really well. Let's translate it. And then fortunately as well, the world is suddenly waking up to it wants to have wearables. I don't know how many companies in India currently are trying to develop a CGM, a continuous glucose monitoring, but there'll be a few doing it. And I may have some slides as well about that market size in a bit. So it's the same science that's working in an IVD application there as is working in the wearable application in the right-hand image. It's the same chemistry, same electrochemistry going on here. So this is the science that can do discrete measurements, or it can do continuous measurements. At ZP, we really think we're part of the IoT of things. So, IoT, there's, the Internet of Things is kind of, if you look at it, everyone has done flow. There's a flow sensor. People have integrated these things with, with web, with apps and with cloud solutions. Weighing things, measuring mass is done. I would say that leak detection is done. You can simply have integrated electrodes. If there's a leak, it completes the circuit and you'll get a signal. That's done, and you can buy products like that. Electric cars, I don't know how many current sensors are in an electric car, but I can tell you it's a lot. So all this is saying is a lot of the Internet of Things sensors are very much done. Temperature and humidity, absolute classic, completely done. But there's a big elephant in the corner on this one. There's a complete lack of biosensors and electrochemical sensors. So that's really the kind of market opportunity. And I'd also say the academic opportunity as well. The world has done everything else. If it's a physical measurement, a condition measurement, an electrical measurement, magnetic measurement, the world has done it. But what it can't do readily is it can't readily make biological measurements, biochemical measurements, and chemical measurements. And I will expand on that a little bit. So if we think about our environment on Earth is made up of generally 3 phases: solid, liquid, and gas. Electrochemistry can actually deal with all of these phases. There's a lot of gas sensors are actually electrochemical. So I am going to focus today on the liquid phase, which I think is much less addressed. And the nice thing about the liquid phase, when you look at it, it can, the human being is, I'm not sure if it's 78% water or something along those lines, but all the solutions that we're full of, be it sweat, be it saliva, be it tear film, be it urine, be it interstitial fluid, be it blood, these are all the types of solutions that electrochemical sensors can deal with. I mean, blood is a classic. If you want to make an optical measurement on blood, you would have to take that blood, dilute it, and then make the measurement. Whereas the glucose strip clearly demonstrates to you, you can take that drop of blood, put it on an electrochemical sensor, and you did not have to dilute the sample in order to get a signal out of it. There was somebody called Elizabeth Holmes in California, and she was developing she wanted to measure everything in blood, in one drop of blood, but because she did it optically, the first thing she had to do was dilute the sample, and then actually they ended up diluting all of the other molecules that she wanted to detect, and so they ran into a really serious technical problem. I think they would have been better off going electrochemical. What makes what we do possible? Well, what makes what we do possible is low power electronics, the miniaturization of electronics, the connectivity through the smartphone. These days now at ZP, we do have a cloud and we do have an API, an application program interface. So we want to be part of that ecosystem. What makes us possible what we do today, and it's done particularly well, I would say, in India, is data science, AI, and tiny ML. And the tiny ML community is really interested in electrochemical sensors. Like I say, I gave a talk this week and they were super excited. I am going to talk about actual applications, but everyone is trying to shrink down what's done clinically into, first of all, it was benchtop, then it was handheld, then it was palm size, and now it's wearables. This is not a idea, this is a thing, and it's all made possible because the electronics got smaller, the devices are lower power. If you stick with electrochemistry, you do not glucose strip need 300 nanoliters. How much sample preparation does an electrochemical sensor need? Maybe nothing. It can just be the drop of blood itself. How much power does an electrochemical device take? Well, here's a wearable device that's running for 10 days, and it does have a coin battery in it, but it's a fairly low powered device. Applications. So at ZP, we work in the food industry. This is an electrochemical device. We have made, and I'm not going to talk about it because I feel like I did talk about this, a year ago, nitrate sensors for the soil. But just to say, electrochemistry, you can make a nitrate sensor and stick it in the soil. It's one of the few sensing modalities that you can do that. I will give some extra data today on measuring glucose and cortisol in fish. We've mainly made some progress on that. Electrochemistry is a very robust science that you can make small packages, implant them in the fish will live, and you will be able to continuously gather data on them. Very interested in putting sensors into the horticulture application. Wearables is something we're very active in, and we still do IVD measurements, in vitro diagnostic type measurements. Like I say, if you've got any questions, don't put them in the Q&A button, and I'll be really happy to kind of answer them. The other part here is that ZP, we have all these sensors. Now, for me, these sensors, I'm not promoting them to you, but I am arming you with this to say that if you ever get a kickback on, why you should be doing electrochemical research or working on electrochemical sensors, these sensors demonstrate to you the broadness of the science and the technology. The glucose sensor is amperometric. The oxygen sensors are amperometric. The pH sensors are potentiometric. We have conductivity in here, which is really a form of impedance. And if we were making something like what I call an immunoassay, we would often use impedance spectroscopy. So electrochemical sensors can achieve an awful lot. They got a lot of modalities of detection, and in here we have large proteins. Troponin I is a marker for cardiovascular. It's a protein, whereas pH is, probably the smallest ion. A proton is the smallest ion on the planet. So it's got a plethora of what it can do. I know this is and everything we try to do, we at least deliver it onto something that's small, manufacturable. This is a screen printed electrode, and we translate most of what we do onto that kind of thing. What I want to say is that one of the things that comes to us quite a lot is people ask us, well, you have a glucose sensor. I want to use that glucose sensor in this application. How accurate is your sensor? But you've got to, I'm sure many of you understand that the accuracy of a sensor is really, the sensor is put into a system. So if I was talking about a blood gas analyzer, you go to the doctor, they take a blood draw, they put that sample of blood onto a carousel on a robotic system, and the blood is taken and they do a series of tests on it. It could be oxygen, that's dissolved oxygen. It could be glucose, lactate, electrolytes like sodium and potassium. So when asking the question, what is the accuracy of my system? I'm sorry, of your sensor, it's actually, I can only answer that question in the context of it's only as accurate or as good as the system that it's actually put into. I'm just going to answer these questions. So I can just see a few questions here. Yeah, so one of the first questions is, how about the shelf life and accuracy of electrochemical sensors? So I know I'm falling back on the glucose sensor, but I'm going to answer it and say a glucose sensor, you can, now in India and even in California and Europe, now we are having extreme temperatures, like 40 degrees Celsius. So this is quite extreme. I would say quite comfortably that a glucose sensor can sit on the shelf for 18 months at 25 degrees Celsius and it will survive it. So I think that enzyme sensors in particular are quite robust. With the problem, we start running into robustness problems, I think, when we start going towards antibodies. So the quick answer is, if I was going to give you the best case scenario, I'd say a glucose sensor, 25 degrees C on the shelf, if packaged correctly, kept out of direct sunlight, will last you a long time. Now, I'm being asked here as well, do you have any options for non-invasive measurements as well for CGM? So the quick answer is, I am wearing a CGM on my wrist at the moment. I will discuss about its modality. It's not non-invasive in the same way that Apple are trying to. I'll just grab an Apple Watch. Apple have spent probably hundreds of millions of dollars trying to obviously use the LEDs on the back of their watch to measure glucose. I can do very specific webinars about that, that they've spent easily over a decade doing it, had quite a large team on it, and they're still working on it. So do I have any options for completely non-invasive glucose monitoring? No, but I think Apple's a useful case study on that. But I will talk about this particular watch, which I'm wearing in the next few minutes. What I want to say is, like, if somebody comes to you and says, well, what's the accuracy of your potassium or your sodium sensor? And I'm addressing my academic colleagues here. The answer is, you can only answer that question in the context of that person's technology. So what's their flow cell? What's their pumps? What's their calibration routine? It's all those questions that really nuance the answer. I just going to very quickly say that, I do like electrochemistry. And the reason I like it is actually because at least fundamentally, we can produce sensors at volume, at low cost, and, it's thick film printing. Now, what makes the biggest problem, I would say, in the R&D phase when people are thinking about screen printed electrodes is reproducibility. It's an absolute nightmare, because what's happening is, this is something that AFTAB and Technando have heard me say verbatim, which is the biggest users of ZP's screen printed electrodes is ZP. So we know the quality and the reproducibility before it ever leaves the factory. Whereas I think what's happening a lot in the world is people are printing and they're shipping, but they're not really electrochemically characterizing this kind of material. But we definitely do, because we are the biggest users of our own products. Configuration. So there was a question just now about, do we have any options for non-invasive glucose monitoring? So here's the epidermis. This is the outer layer of your skin. This is the dermis, which is kind of underneath, if the epidermis is this kind of layer of dead cells, that's the sort of uppermost layer. Underneath it, you've got this kind of more live region. Now, the glucose that you're trying to get to is in the kind of dermis and the subcutaneous. So at the moment, we have transdermal glucose sensors. This is a electronics patch. These sensors, the sensing element is about 7 millimeters long, and it goes down into the body. And you have an enzymatic reaction here, which is converting glucose into hydrogen peroxide, and that's what we're reading. Now, what I'm wearing is a microneedle array, so it's not as invasive. It's, for example, these needles would not be more than 1 millimeter long, whereas this wire is 7 millimeters long. So there's a big difference. And it's also probably worth saying that when you try to implant one of these sensors, when I say one of these filament sensors, it comes with what's called an applicator. I do have a few about 1 meter from me. They have a large spring in them, and they plunge that thing into your arm. I think it's perfectly fine, but I can understand it depends on the size of your arm and your pain threshold. This thing, you do not need to plunge it. You just press it on, and the needles go in. The most non-invasive technology that we at least have at ZP is measuring things in sweat. But whether you measure, I would not suggest to somebody that they necessarily measure in glucose in sweat, because it's not clinically proven. You're giving yourself a big challenge, which I think in academia is a challenge you can take on. But if you were doing a startup company, I think it's too big a challenge for you to, because you're going to have to persuade the regulatory authorities that measuring glucose in sweat is good for controlling type 2 or type 1 diabetics. It's a tough clinical challenge for you to do. Something that we are working on at ZP, and I will talk about it today, and it will be new material that's not been covered in these kind of webinars before, is an implantable sensor. It's too short a slide, but I do want to say that the kind of lab techniques that were traditionally just lab techniques, like amperometry, like voltammetry, like potentiometry, and like impedance spectroscopy. Actually, this is a product that we now sell on our web store. It's called a single purpose. It's not a great name, but I think it's sort of single purpose biosensor circuit. These methods that you were once upon a time only, especially impedance spectroscopy, only able to do in a laboratory setting, we can now do in a form factor like this. So that those electronics are in this particular watch. So that gives, I like electrochemistry because actually it's got all these techniques. And I also like it because actually now we're able to really shrink down these techniques into something very wearable and low power. Can I just say to my colleagues that are more kind of interested in sometimes data science, etc., if you're working with teams that are doing biosensor development, encourage them to use techniques like voltammetry and impedance spectroscopy. It will give you more features than boring old amperometry or boring old potentiometry. I know it's a sort of side note and it may be a bit cryptic, but amperometry and potentiometry were techniques that were generally used before modern electronics, before we were able to do voltammetry and impedance spectroscopy in wearable formats or IVD. So I would always encourage these days, actually, if I was making a glucose strip, I wouldn't necessarily just use amperometry. If I was trying to be really fast, maybe I would do it. But if I was trying to be fast and some greater accuracy, I would go for a more complicated waveform and voltammetry, or something called pulse amperometric detection would be the kind of direction that I would be going in. Voltammetry is something that we do an awful lot of at ZP. We use it a lot in the food quality testing technologies that we use. I'll bring this slide up later on, but this is something that we've been developing and testing. This is measuring gingerol, and I just use it to sort of say that once upon a time you would not have used electrochemistry and especially voltammetry to measure natural products, but this is something that we do quite often. And here, all we're simply doing is changing the concentration of the analyte, and obviously just measuring the peak height or the area under the curve using a voltammetric method. And we can essentially build up a calibration curve. I'll bring this point up later on, but each one of these data points is a triplicate data point. So we're testing at the highest concentration on 3 electrodes, and we're testing at the lowest concentration on 3 electrodes, and we're testing the middle concentrations on 3 electrodes. And you'll notice that our signals are very similar. If you try to do this on, this is a plug for Zimmer Pico. If you try to do this on some screen printed electrodes, the signals will be very variable. And that's the big problem that's holding up research and development, is because the fundamental materials upon which people are building are not repeatable. So our speed to market and our speed to development is actually because we're making a really repeatable electrode. And this data, as I say, is 18 data points here, 3 at the high, 3 at the low, and each one in the middle is also 3 data points behind it as well. And that's, for example, done on one of our screen printed electrodes. I am going to talk about continuous measurement, which brings back to the CGM points earlier on. I can see there's some people have put some questions in chat, which I didn't really see. So in fact, there's lots of questions in chat, maybe. Thank you for joining. That's from Aftab. Somebody's asking a question here. For an existing immuno-based electrochemical sensor, if I change the source of antibody, will it need repeating electrical studies for calibration curves, etc.? So their question is this: look, I'm making an immunoassay. So that means that they've taken something like a gold electrode or carbon electrode, they've put an antibody on top of it, and they're testing an antigen. Now, if they change that antibody, I got a horrible suspicion that they'll have to redo their calibration curve. We would end up just doing it anyway. We would have to just do it, even if we thought that it was low risk, it still is a risk. So I hope that helps to answer that question. In my opinion, we would redo it. So I will talk about in vivo embedded electrochemical sensors, and I'll talk about ex vivo or wearable sensors as well. So let me just do a quick case study. This is a technology, we call it fish tag. This is really similar to there's a couple of companies on the market at the moment. One's called Medtronic, the one's called Dexcom, and they make a glucose sensor for type 1 diabetic. So this is the package that we have, and this is the sensor. That sensor element is really similar to Medtronic and Dexcom. We have it in a couple of flavors. We have it in types. We have glucose and we have cortisol. And in that package, we have power source here. We have the PCB, which is a single board potentiostat, if I can say. And we also have a transducer for sending data out of this package so that we can do essentially remote data collection. It's a very small thing, but just to say that in this next image, this is a fish. It's not a dead fish. This is a fish that's under sedation. So literally, they have actually, the fish is alive. It's under sedation. The vet is given it is opening up here, and actually they put the entire package into the fish, and then they suture or stitch the fish back up. I'll probably explain that in a minute. Now, these are those fish. So these two fish have undergone that procedure. So these fish are swimming with electrochemical packages actually in them. Somebody wants to say here, how can we know the cause of noise doing a voltammetric analysis and how to avoid the same? This is my opinion. If you're doing a voltammetric experiment, you've got noise. Sometimes it's the mains electricity. I have seen this where you're actually plugged into a circuit within your building has got noise on it, and you're not if it's our instrument, I apologize, but your instrument is not properly isolating you from the mains electricity. But for me, really, the biggest source of noise I would actually suspect is connection. Everyone just doesn't like this answer, but if you make poor connection to the electrodes, you will get noise. So at ZP, we make we do use crocodile clips or alligator clips, but those are a real kind of, you've got to get decent connections, which is nice because actually I finished this presentation with some decent connectors, if I can say. So I think in voltammetry, if you've got noise, if it's spiky noise and it's got, when I say spiky, it's going up and down quite a lot. That's, let's say relatively high frequency noise. It's probably poor electrical connection is my super suspicion. These fish have a full electrochemical sensing system plugged into them, or not plugged into them, inside them, and we're gathering data on them in real time. Aftab is part of our internal team, so he knows who So and Evan are. So the fish are named after our quality manager and my business partner. And like any good business, the quality manager is a lot more active than the CEO. If you look at these two fish swimming away in the tank. And as I say, we've actually got the full package inside these fish, and we're able to get really decent data out of it. This is something I would just want to say, in particular in India. I think you do have a extremely, I'm talking, hundreds of years, thousands of years of, maths development, and I think that still culturally goes on very strongly. So you can see that here we've got two data streams here: the raw data stream, which is extremely noisy, and let's say the median points, which is the true, let's say, signal when we remove the noise. So you do have to understand that once you start putting sensors into fish, as an extreme case, you will get lots of artifacts, and you do have to have a very strong data science team to help you deconvolute the true signal from the noise. And something like ZP, that's what we have, that's what we do. And that's a sensor that's been in a fish, and we've continually monitored its glucose level for example, 9 hours. This is a slide that I do give at our workshops. I don't mean to patronize this audience. I think that a lot of you are very familiar with this, but this is essentially how we would build a glucose sensor, the different layers that we would use, and there's an enzymatic reaction that kind of takes place within the layer. And there are what we call generation 1, generation 2, and generation 3 glucose sensors, and I am in particular talking here about a generation 1 glucose sensor. But what's useful about electrochemistry is that science, we can both use it in that implantable sensor, or we can actually also translate it into something like these microneedles. So this is a CGM smartwatch. I'm going to refer back to the previous question. This is not a completely non-invasive CGM solution. This is a minimally invasive CGM solution. It's using the same core science that at least I've been involved with for at least 23 years, but it's a new form factor, and it's a new form factor that's made available because it's a very repetition of something I said earlier on, but we are only able to do this because of modern electronics. And I'm really looking forward to actually India in particular, really getting into the semiconductor industry. That's going to be really interesting for us all globally, to be honest with you. Side note, but I think that's actually really quite exciting because, with all the sort of high level of education and all the brain power, that should really make a big difference. Anyway, back to the point. We can only do this kind of work actually because of the sort of shrinkage of electronics. I think I show it here that this particular CGM technology, this is an important design input for anyone who's kind of thinking about making wearable sensors. It has at least two parts to it. It has this watch and it has the sensor. The reason I'm emphasizing this point is, don't develop technologies where the electronics and the sensor are completely integrated. It's not going to be acceptable to have to throw away a battery, the electronics, and the sensor after 10 days of use. Regulation is going to kick in and says, no, you have to minimize your carbon footprint for your product. And so this product intrinsically has at least a recyclable component built into it. That's the sensor, that's the bit that's going to get on the skin and is essentially going to get mucky. And if you wear something for 10 days, it's going to get pretty mucky. But the electronics are recyclable. So that's a design input. I know this is a talk about electrochemical sensors, but I can't help but talk about commercial perspectives as well. I think the glucose strip market is actually going to grow in India because I can see that obviously people are very interested in manufacturing glucose strips in India. So this kind of 3% decrease in the global glucose strip manufacturing or market size may be bucked in India, but in the longer term, everything's going over to CGM. The continuous glucose monitoring is the growing market, and I think it really it generally adds benefits to the individual diabetic and to society in general. People's glycemic control improves when they can continuously see their data, as opposed to pricking their finger, which is an effort in itself. and then they may only get 1 data point per day. They can't really control their glucose that way. This is just a return to, that we have this watch, we have these sensors, we have this packaging. And back to the question, and I know it's a repetition, but it's not non-invasive, it's minimally invasive. If you are going to do minimally invasive, I would suggest that you have to build a company the size of Apple and have that kind of resources to even take on that problem. And I know there's companies that, there's always a company trying to do a non-invasive glucose measurement. This is what it looks like if you zoom in on the skin. But before you think, oh, that's horrific, don't forget these are the hairs of my arm that you can actually see here. So it's, we've really zoomed in there, and you can see the little sort of marks on the skin. I can see that Aftab has asked anyone if you've got any questions to put them in the Q&A section. I know it's a little bit complicated. There's a chat section and a Q&A section, but we'll try and pull out the questions in real time as well. It's interesting to say that this watch, I mean, the reason I can talk so freely about it is because it's protected by over 50 patents. And I think 36 of the patents are around this idea that you've got a microneedle technology. The microneedles are sitting in the interstitial fluid. We have a clear chemical reaction, the conversion of glucose essentially into electrons through what we call an enzyme cascade. So we get to our electrons. We really benefit. Somebody can't see the Q&A section on top, but I can promise you it really is there. It's next to view and next to notes. So there's a chat, there's people, there's raise hand, there's react, there's views, and then there's Q&A. So there's a 36 patent portfolio here, which talks about microneedles that sit in the skin. There's a chemical reaction. The chemical reaction produces electrons. We have a very, at ZP, we do actually make these electronics available. We call it the single-purpose biosensor circuit. And then we are using kind of machine learning to help us interpret these signals. We can display it on the smartphone. We can make Bluetooth connection to a smart device. And then we'd actually have a full cloud system called Julie, which is able to receive electrochemical data. If people reach out to Technando and say, look, we enjoyed the webinar, reach out to them, suggest what they would like next time, because I'd be quite interested in talking about Julie and its ability to collect and analyze data, but I'm not going to be able to spend a super amount of time necessarily on it this morning. I'm going to slightly change direction, only just slightly now, because I started off with this talk saying, okay, it's a bit of a technology update, bit of an opinion piece from Zimmer Peacock, and I have gone a little bit into implantable electrochemical sensors and a particular wearable electrochemical sensing technology, which actually happens to be mostly configured for CGM. I'm now going to go to point of need testing. So I know that in India, for example, I follow many of your academic institutions and many of your companies, and so people are very interested in measuring things like nitrates. Monitoring is going on, and so this is a kind of point of need testing. So it's not continuous; it's discrete measurements. This is, first of all, I'll just describe the sort of technology stack that at least we have, and I'll show you how we're applying it. But I want to say that I'm very keen, especially my academic colleagues, to sort of build using some of our science, actually, because then I think we can really translate it into products quite quickly. So first of all, let me just describe, the technology stack that we have. So we're really good at making screen-printed electrodes, and we're really good at functionalizing them with antibodies or enzymes, ionophores, and turning them into biosensors. We're good at that. We're very good at the electronics. So if you're doing lab work, you're in academia, if it's voltammetry, we don't mind. If it's impedance, we don't mind. If it's amperometry, we don't mind. If it's potentiometry, we don't mind. This electronics will do it all. What allows us to do all of that is we write apps. We have an app on the Play Store called Sense It All, and that one app will very quickly, just using a single QR code, we can actually make it change its method file. So the app works also with our cloud. So I'm not going to talk about Julie today, but Julie can receive all electrochemical data. And so we put our sensors into this electronics. The sample goes onto the sensor. The app tells the meter what to do. The app gets the data back and it sends it to Julie. And on the phone in real time, we'll give you the concentration. But we'll also put the raw data into the cloud as well. So I want to give you, so first of all, I think people know this, but I just want to give you a sense of why you should even care about nitrate. So nitrate is a big global problem. First of all, nitrate is needed, whether it's ammonia, nitrate, urea, these are all sources of nitrogen. We do need these, let's say, molecules to fertilize the ground so we can grow enough crops so that everyone, on the planet can eat. So we benefit from it. Problem is that actually the nitrate production produces 1.2% of global CO2. So if we want to make an impact in global warming, reducing the nitrate production in the world is going to be important. 1% of all energy that we consume on this planet goes into nitrate production. I think it's called the Bosch-Haber process. It's very energy intensive. We do need the nitrate or the fertilizers, but it is energy intensive. They think that 67% of nitrates are wasted, and I not know, but there's not a river in Europe, USA, the large rivers in India which are not polluted with nitrate. They are all polluted with nitrate. That tells you that the farmers do not want to waste money. Why would they want to do that? But they simply don't know, how much fertilizer is necessarily in the soil at any one time, and it leads to local pollution. It leads to acidification of soil. It can also lead to toxicity in people, and it's a bit of a, let's say, a bit of a problem. So my argument is, and I've seen it happening in India as well, that actually we're able to take our technology stack, and we've done that, and we're able to reduce the problem down to, in fact, I'll let the engineer run this. So what's happening here is they've got the SenseAll platform. They scan the QR code. The QR code now tells them, look, this is going to be running a nitrate assay. They take the nitrate sensor and they put it in the meter. In a bit, they're putting in their credentials here, but what they're up to is they're making sure that data goes to the cloud. So you don't only get the nitrate, let's say, result on the phone, you also get the nitrate result in the cloud. And that's really important because later on, if you want to confirm the quality of that signal, you can do it by going to the Julie cloud. So what the engineer is doing here is, this is really a point of need test. Look, she takes the sample, she puts it onto the sensor, she runs the app, and this progress bar, it is literally doing an electrochemical measurement, and it comes back and says the nitrate concentration is 9.94 millimolar. Now, this video has a second part to it as well, that actually will also show you that it went to Julie. So Julie is a cloud system that ZP has built easily over the course of 8 years, and the nitrate data is up in the cloud, and we can go up there and we can actually investigate it later on. So that's a really useful way of doing, when you're doing development, ask the question, where's my data? Even when you're done development and let's say a farmer was running, or the local authority was running a test on water quality, later on you can actually get the raw data, and that really helps with ensuring that you don't get false positives, false negatives. I just want to say, I'm just going to silence her for a second. Just to say that it's not just nitrate and glucose and things like that are actually addressable by this kind of technology. This is what's called total antioxidative status. Total antioxidative status is a good way of measuring the shelf life of food. If food has a high total antioxidative status, then it has a longer shelf life. If you leave food standing, its total antioxidative capacity actually goes down, and actually it has a shorter shelf life. So this is a TAS sensor, but it's just saying it's the same technology, same app, but running a different method file, but this time it's a different sensor. So it's often just the method and the sensor that change, but otherwise we're using the same technology. I appreciate I've got sort of approximately 15 minutes. I will just have a quick look at the Q&A, make sure I didn't miss anything. Nope. Cool. I do appreciate the thumbs up. Thank you guys for thumbs up on those answers. As I said at the beginning, and Aftab knows me well as well, that, if you've got any questions, just ask them in real time. There's no big sort of issue. I want to talk about commercialization here, and I want to talk directly to my academic colleagues or my sort of lab research colleagues. What does a glucose product look like? A glucose product, or sorry, not glucose product, I should say electrochemical sensor product look like? It looks a bit like this, that we have often a disposable strip. Disposable is good because you don't have to worry about sample to sample contamination. I don't like the carbon footprint, but you put the sample on there, you get the measurement, you then get rid of the problem of the next sample contaminating the first sensor. So there's a good business reason or good technical reason for that. But this is what a product looks like. It has a strip here, it has a meter, it's all pretty small and handheld. That's what we're aiming for. That's what at ZP, that's what we're aiming for. And so I think that we do have to look at the hardware that we're actually using in the lab, and ask ourselves, are what we're doing in the lab, am I making the job of translation to real products as easy as possible? So when you look at, this lab setup here, I think there's at least 3 problems, but I've listed out 2 of the problems here. The first problem is this is the electrochemical cell. It's this kind of pear-shaped glass vessel with some big electrodes stuck in it. That just mentally is not what a product looks like. It's simply, that's not an electrochemical product. An electrochemical product or sensing product really looks like that. So I think it's almost like a mental thing that when we work in larger volumes with glassy carbon electrodes, platinum discs, gold discs, we're removing ourselves from the real world. If this is going to make it to market and really make an impact, we have to get closer in the way we do our science to what the market's really going to be able to produce. So we just never use these kind of disc electrodes in fact, I have used rotating disc electrodes. I never use them these days because they're too far removed from making a real product and making a real impact. The other thing that's going on here, this is, we do own these kind of instruments, but they're single channel instruments. So in real biosensor development, you have to be doing a lot more testing, and one test at a time is just never going to give you the throughput to have the confidence that this system is really working. So this kind of traditional, this is exactly the way I would have done my PhD. This kind of, but that was a while back. This kind of setup is, for me, 2 problems. The setup looks nothing like a product. The instrument is single channel, and the third problem I actually have with it is that the volumes that these kind of setups require is just too big. It's a waste of materials, and the phenomena that you get when detecting or testing on 10 microliters is very different to some of the phenomena that you'll get when you're testing at 50 milliliters. So the science itself has to actually look like the products that we probably ultimately need to be making. So I do have a problem with this kind of glassy carbon electrode. I'm biased, but use electrodes that are kind of representative of, let's say, the final application. Why? Because it makes people like my job easier. And I think in India, there's always an entrepreneurial spirit and a desire to make your own product. So start off the research on materials that look like, let's say, the final product. My second problem was the amount of testing. So we do need to go parallel in our testing. Just this simple, let's say, calibration curve alone was, 18 tests were done here. So even if labor is low cost, you do need to have quite a high throughput of testing. And I think just single potentiostats really, or single channel potentiostats really don't cover it. I mean, this is an example of some work that we did. It was impedance spectroscopy. We did over 270 tests. Now we did that in it probably something like a day, but we can't do it unless we're doing parallel testing. So I'm obviously a big fan of using screen printed electrodes. If you're making an IVD device, an in vitro diagnostic device, use small volumes. Don't stick the sensor in the solution. Put the solution on the sensor. That's closer to what the real world product will do. There was a very nice question earlier on about noise on the voltammetry. nobody likes this answer, but I think it's generally noise on voltammetry is generally the connectors that are the problem. So this is one of our connectors, and we've made a really big effort to actually make sure that the connectors are good quality. We have a whole range of these with different size orifices here, because if you have a ZP potentiostat, then our banana plugs are 2 millimeters. If you have a palm sense potentiostat, the banana plugs are 2 millimeters. I think if you have a CH Instruments or an Autolab, the banana plugs are 4 millimeters, but you need a decent connector between your potentiostat and the screen printed electrodes. And then this is the last thing that's sort of, I will cover it and I will be, but we are developing and using in-house now this particular parallel little potentiostat. It's 6 channels. So you could see that I showed an 18, I showed a calibration curve earlier on that was done. It was 18 data points. You could see that we could do it in 3 runs. We could get all 18 data points just on that single instrument. It's particularly cute because it's actually just so small, but that allows us then to do 6 electrochemical measurements in parallel. So my request to definitely my academic colleagues is work on platforms that are representative of products, and please work in parallel more, because then we can start answering questions like what's the repeatability of the test, etc. So if I was to summarize, once upon a time you'd have to argue why biosensors were important. I'm not going to argue it anymore. The world is changing. COVID-19 proved that rapid diagnostic testing was really a needed thing. If you're here because you want to be persuaded that electrochemical sensing is the best science in the world, I think just look at the biosensors that we're able to produce. I would ask just really politely that, if we're doing lab work, that the lab work is representative of the products that we have in mind. And I'm really excited that as a science, we are actually able to make products like this in a sort of wearable format. And for me, I did do my PhD using carbon disc electrodes, and I did use rotating disc electrodes, and I do sponsor PhDs these days. And when I'm sponsoring the PhDs these days, I make sure I just ship them the screen printed electrodes, because then it breaks them. Immediately they're like, oh, there's the electrodes, get on with it. So I just want to say thank you to you all. Like I say, any questions, give AFTAB some follow-up, let's say. And I'm also going to say that I'm going to list this on the website pretty soon. When we finish this, I'll get a recording, and I'll put the recording online, so hopefully you can sort of rewatch it in a bit. And I should really just say thank you very much to AFTAB for basically doing all the organization. So thank you so much, AFTAB. If anyone's got any more questions, I'm happy to answer them. I know that we were essentially running for, we put up this for 60 minutes. So I'm happy to take a couple of more questions. I'm just looking around the chats. So I'm looking in the Q&A. I do see a couple of questions in there, but I think we answered those ones. And if I look in the chat, right, okay. So I will answer this one. Is coating the electrode surface with carbon nanotubes recommended on screen printed electrodes? Does it? It's interesting. I've done a fair amount of work with a gentleman called Richard Compton at the University of Oxford, and for a while there he was definitely using carbon nanotubes and single wall carbon nanotubes. I think what carbon nanotubes do for you, you've got a carbon surface, it has a certain surface area, you add some more carbon nanotubes onto it, you've basically kind of gone from a sort of a more flat structure to a more 3D structure. So it could end up giving you some more sensitivity, but for me, it doesn't add a lot of value. It's never made us go from I cannot sense this to now I can sense it. I think it's an incremental improvement. And what you're actually doing then is you're also introducing a new process step. Every time you have a process step, you introduce a source of variability. So making a screen printed electrode, for example, is a variable process. So we try to control that. When you then do a deposition of carbon nanotubes, you're now introducing a new process. So the variability of, let's say, a batch of 50 sensors will go up because each time you do a deposition, you are introducing a source of noise. So it's fine. I'm used to it. If your PhD is going in that direction, pursue it. But it doesn't make the difference between success and non-success in a commercial application. Somebody did ask a question here. Does only the paid version in Julie support importing electrochemical data? No, there is a freemium version, and I believe you can do something like 5 imports. Julie's been coming for a long time, and we've been using it for a long time. Really understanding what freemium versus paid is, and I'll be frank with you, it's something we're still figuring out. But you can import data into Julie even on the freemium version. I appreciate the question because what we're trying to do now is hold a webinar every Tuesday, and it is recorded at 8 a.m. and I think it's Tuesday, 8 a.m. London time. So it'll be recorded to start answering questions about Julie. So we understand that Julie's is a product's been 8 years in development. It's got a lot of features, and there's no way you can you document in it, or it'll produce a book this thick. So it's a good question. The quick answer is I think you can. If you struggle, contact us. But if you've got a ZP potentiostat or you've got a PalmSense potentiostat, you should be able to just upload the data. But have a go and give us some feedback if you're struggling, because the biggest users of Julie are us, but I'd like to hear some other people's experience of it as well. Oh, there we are. Somebody's currently using a PalmSense 4. How to ensure coating on all electrochemical sensors for CNT coating? How long should we leave on the electrochemical surface before analyze it? Currently, I'm using a PalmSense 4. So first of all, PalmSense 4 is a fine instrument. It is compatible with Julie. I think my only concern with it is it's single channel, so it limits your data. Your next question then is really about coating. So if I was going to do that coating, I would just be doing drop casting using a pipette. We would actually use a robot, but the robots cost like $100,000 US. So I'd replace you can use a pipette it on there. Now those carbon nanotubes are going to stick to that carbon quite quickly. So if we can call it incubation time, if you put a drop of, let's say, 3 microliters on top of one of our carbon electrodes, you've just got to estimate how long is it going to take me for those carbon nanotubes in my solution to make it to my surface and then stick to my surface. So I'll give you, we would potentially actually just let the drop evaporate so that everything came down onto the surface, and we may then wash it to get rid of non-specific binding. And it's nice that actually, Aftab's put a link up to Julie. So carbon nanotubes, quick summary: drop casting is fine. I know it works. Maybe let the drop evaporate, especially if you're doing on a screen printed electrode. Maybe do a wash afterwards to get rid of non-specific binding. But most of those carbon nanotubes are going to love sticking to the surface. Aftab, if there's anything you want me to particularly cover, I will do. Otherwise, I'm sort of happy to take another question, or happy enough to let people get on with their day. I'm not sure what time it is for you. I think there's a 4-hour time difference between us. But I suspicion it's about it's about maybe 5 p.m. at your time.
It's 5 p.m. here, Martin.
Great, cool. Is it okay if we wrap up for today, Aftab?
Yeah, I hope we are done with all the questions from the audience, and soon we are going to send everyone the record of this webinar as well. If you want to go through the missed any part of the webinar, you can just watch at your ease.
Yeah, exactly. And if you think that if there's things that you want to cover, reach out to Technando, because I'd like them to put a list together of things that maybe we can cover in another webinar, so be more specific that the next time about people's actual needs. So maybe we will do, if there's enough interest, we'll do it in a month's time. But I think we look to you guys who are here today to kind of give us feedback and give us some guidance. There we are. Somebody said I'd like some more webinars, so there you go. There's one data point for us. Right, Aftab. Well, jump off and do some more, let's say, meetings. But so thank you so much for organizing, and thank you so much for everyone attending.
Thanks a lot, Martin, for your time. Have a great day ahead. Bye-bye.
Cheers, and congratulations on the moon landing. Take care, guys.
Okay, thank you.
Bye-bye.